And after the well is drilling and also fill the materials, the top of the 3 meter of the borehole, commonly they will using the seal system to stop the contaminations moving into the water supply from the surface. Because commonly the contamination is from the surface, like when you have the rainfall, they might wash in the material and then flow into the downhole area, and they'll be easily to be contaminated. And commonly they use the concrete to put out between the casing and also the edge of the borehole. And from there, the ground around the hole need to be dug down above the feet and then cross the rock of the breakage packed into the depth of about 6 inches. So this is based on their criteria. It's not exactly like that. That depends. And it is then time to mix up with the concrete and then create a circular platform around the well. The concrete need about 10 days to harden. So they use in these kind of systems. So when you have the water flow out, they will be able to directly drainage to the other places. So that's their rule to do this work. And commonly, they doing the concrete on the surface, so they try to seal that. And then they will put a pipeline inside. Because they were using the hand mat, the pumpage, they are not using the electric, because in this area, commonly they do not have the electric. So they need to use the hand mat pumpage for that. So they install the system here, and then the top will install the head, okay, to do the work. So finally, a hand pump needed to be installed. Our partners as this hand pump, because they are locally available and also have the pump over many years, they are durable and practical. Rising main is installed down the plastic casings. That is much smaller tube, about 1.5 inches in the diameters. So they put it inside, okay. And above the bottom, yeah, so there'll be some systems, okay. Yeah, I think we don't need to go through all of that. And after that, the water can flow. After you have that, when you have the hand pump, you will be able to get the water. So that's the final pictures. Okay, so after you have the hand pump, you will be able to have the waters out. So there's one of the water projects they done in Africa to help them finish this kind of wells for the drinkings and irrigations. And after the system developed, okay, they will need to have the firing. A picture of water flowing from a new well is the beginning, not the end. It is the beginning of a few new way of the life for community, and it is beginning of our measuring the outcome of what we do. Most simple monitoring and evaluation is about making sure that the work we do is the best that we can do. So try to have the continuous monitoring, or have some of the people to take a look at the situations and evaluate if the water is okay. And if more safety, commonly you will take the water samples to analyze, to the lab analyze, to confirm if they have the metal contamination or not, like arsenic or some of the others. Is that toxic for human or not? It is vital that people involved in development have ways of finding out the impact of their work from the community they serve. Monitoring can be as simple as going back to the wells periodically to be sure that it is the work. It sounds easy, but it requires time and money for things like fuel to travel from site to site. And for the maintenance, commonly is the difficulty, because if a system is free, if the system is free, you don't need to pay money. Sometimes people will not feel that's deserve to protect it. So you will be arbitrary to use the system. Yeah, the same like in lab or in the university. If you feel that's for free, you will waste resources. Sometimes you will waste the resources. You do not trust there'll be the resources, the natural resources, and that belong to all of the peoples there. It not belong only to you. So after doing these kind of settings, it's for free. But if you do not try to protect it or try to maintain it, or you just arbitrarily use or just kick, they might easy to be broken. Okay. Yeah, but sometimes it's not easy because we don't know exactly how people do the work. And they will not, after they construct the wells, they will just leave. They will not stay there for a long time. Okay, they just put the service. And following is the material we already mentioned before, but we repeat some of the contents. It's published by Hydrogeological Survey or GSMMA right now. So the main, this project is mainly for the, I mentioned, for the mountainous area. So one of the projects we already see for the hydrogeological borehole data in the mountainous area is done by this kind of project work. And this one is mainly to install the observation. So the previous that we see the borehole design is the same. Okay, so we have seen this before. We will have the well design, and there will be design table. After you do the survey, you will have the material or have some information, and then you will make decisions where to install your stream and to do the observation. So that's what we already see before. We were using the loggings, and we using the camera and using the Packer test to estimate the hydraulic properties. And the well design, very quickly review. We have this is the screen. So we put the gravels outside, and they will be above several meters and bottom several meters. And after that, we pack the fine sand or the coarse sands, and then we put the bentonite above. And we were able to prevent the shallow water to flow into the deeper system, or the deeper water flow into the shallow system. Because commonly they could be quite nearby, or even some of the borehole for the WIA. They drill in a big hole, and they put the borehole in different depths and seal the central. Okay. So you need to seal well, and then to prevent the connections between different boreholes, because we hope to observe the specific depth for the water level or for the water qualities for that. Okay, so there's a previous very quickly review. And following is the well constructions. We using some of the machine to do the drillings. So this is one of the drilling machines. So you can see that this is like a small trunk, but they connect to this kind of pipeline, and they'll be able to do the rotated injections. And they'll be like this is the steel pipelines. They connect one by one to do the continuous drillings, and there could be several diameters. Some of that will be, like I mentioned, the casings is outside to protect the collapse, and the inside will be another small one to do the drillings, the drilling steam. Okay, so they will be separated. So there will be the videos. This is the drilling jumbos. So they take the photo, and the camera is taken by me. So this is the outside part. They're using that to protect the collapse. As I remember, I forgot exactly the detail. They should have the two, as I remember, they have the two kind of the size. This one is larger, or maybe they have the small one, or maybe this one is already the drilling bit. Okay, they have the one of that is small one, the drilling steam, and the other could be like this one is the larger one. So they're using that for the drillings. So they rotate. Continuous to rotate, and they will have the drilling bit at the front of the first steam. Okay, so they continue one by one to put inside to do the drilling. And that's very heavy. One of the steam could be over 100 kilograms. Okay, so very heavy. This is the control. Rotate control, so they continue to rotate. And some of the this one pipeline is for inject the airs. So this kind of jumbo, they inject air, not the waters. They using the air to be the fluid. Okay. And the water that you see is the groundwater. When they drilling to a specific depth, they have a groundwater layer, so the groundwater will be eject out. But when they are very shallow, they will not have the waters because they are dry condition or the unsaturated conditions. And this one is a very strong groundwater outflow. Okay. This is the drilling step, remaining control the drillings. Yeah, but this one, because they have the very strong groundwater system, so they continue inject the airs inside. And if the water is very huge or the water supply is very large amount, so they will have erupt. Okay, yeah. So this is the drilling bit. So they continue use that. So this is the drilling, and they were using the plastic to prevent the erupt of the waters. Okay, but it's still very strong. Okay, and this is in Ali Mountain. This area is the park of the Ali Mountain. And here is another drilling systems. It's a very small one. Also the rotator system, but because this area is not easy to have the big machines to go inside, so they using a small drilling machine to do the drillings. And the drilling bit is around this size, yeah, like this kind of size. This is the drilling bit. So they using this one to cut your rock and your rock or the sediments. This and the other do not have the drilling bit, so the other only have the steam. So they just connect one by one to do the drillings. And after you finish the drilling, this is the wells. The well is smaller than the pipeline that you put inside, because after you finish the drilling, you need to put the wells inside. So this well is around, as I remember, maybe 2 inches or 1.5 inches. Okay, and they cut several holes here to become the screen, and using the net to cover that. Also, although this is the very rough methods to cover the screen. Okay, so after the drillings, they will put the wells inside to a specific depth, and then they are able to do the observation. And this one is another, I mentioned the impact drillings. This is the drilling bit. So they are not rotate. They're using the impact, the gravity impact. Okay. So after they continuous impact, because they are very heavy, and you can use the impact to continuously do the heatings. But this kind of the drilling is very, very slow. So you can imagine they just using the gravity. So they just the up left and then release, pang, pang. So one day maybe just several meters, maybe 3 to 5 meters is the maximum. And as I mentioned, that if you have a boulder or a very big rock or gravels, the rotate, like a previous rotate machine, is not able to do the drillings. So you need to use in this kind of impact to destroy the big boulder, and then you'll be able to continue the drilling. And this area commonly in the very shallow, they are uncemented rock or the gravels. So uncemented gravel system, commonly they use in this kind of the impact drillings to penetrate the shallow depth, maybe 20 meters or 30 meters. And after that, the deeper one will be more rigid, and then they will be able to have the drillings, okay, the rotated drillings for the work. Okay, and this one is the casing, although it's not easy to see. This one is the casing to prevent the collapse. I mentioned that. So the size will be larger, diameter will be large. And the pipe bearings, the pipeline. So this is the photograph. Normal one is like the wells. After you finish the drillings, we will put the pipeline inside, or we will put the wells inside. And normal one, you do not have the screen, and this one have the screen. Okay, so this is relatively expensive. They cut four directions for the screen and allow the water to flow in and flow out. And the other is the complete one. They do not have the space for the water flow in and out. And when they put the wells inside, they will mark the number. Okay, because they need to check how many will pipeline or this kind of system be put inside, because for the contract they need to count the length, if the length match the requirement or not. For example, this project, if they require 100 meters, and one well, if the 4 meters, one pipeline is 4 meters, so you need to put how many? 25 pipeline inside. So they'll count 1, 2, 3, 4, 5. to confirm if you really put the pipeline into the specific depth to match the requirement or not. So they'll mark 1, and after put inside 1 and then connect another 2. So this is the connections area. So they'll mark 2 here and then put continuously and to 19 and 19 or further. Okay. So this is the method. They try to put 1 by 1. And my work at that time is to watch if they put a sufficient pipeline inside. Okay. So I need to take photo for each of the pipeline. So this is the screen. The previous from the material, and this one is taken by me. So this is the screen, the same screen, and this do not have the screen. Okay. So here 3 and 4, and this is the pipeline, and this one have the pipeline. And as I mentioned, that commonly the first pipeline do not have the screen. They are for the sediment deposit. Okay. 沉泥管 sediment deposit. So the first pipeline do not have the screen, and then the second 2 further will have the pipeline. Okay, they'll keep the bottom one to don't use in the screen, because when you have the screen, that means you need to spend money, spend time to do the cuttings. So pipeline with the screen is expensive, and do not have the screen is really cheap. So you will not cut all of the screen. Pipeline have the screen. Okay, you cut the sufficient one. Okay. And after that, between, you can see that this is the casings, and this is the wells you put inside. So between the wells and the casings, or the empty borehole, will fill the materials, gravel. And this gravel is not large, so this is $10 NT dollars. So you can take a look at the size. It's around several millimeters, or even maybe reach 1 centimeters. Yeah, that quite depends. So put the gravels between this one, and you'll be able to have the material. Okay. So after you, as we mentioned that in the well design, outside we put the gravels, and then we put the fine sand and put the bentonite. So how can you know if they reach the design or not? We commonly need to use in the measure, using the rule to do the measure, and the rule, the bottom is the heavy one. So you can put inside to confirm if the backfill reach your design or not. Okay. So using the measures. And as I mentioned, it could be some of the different material, and this one is fine sand. So you put the fine sand inside. And this one, I'm not sure, could be gravel or others, the bentonite. Now next we'll have the others. Okay. Now, so we're using, this is taken by me. So we put the gravels here and doing the measurements. Okay, like that. And this one look like gravel, but this one is not a gravel. You can see the color is a little different. This is white color. This is a little yellow color. This is the bentonite. This is gravel. Because the bentonite, as I mentioned before, bentonite is the clay. You can imagine that if you put the powder of the clay in the wells, they have the waters. For example, the water level depth could be 10 meters, but you need to fill to the bottoms. Your bentonite need to put in to the bottoms. So when you using the powder of the clay to reach the water, they'll stick. They'll expand and stick at the shallow depth. So it's not able to use in this kind of work. So they'll put the bentonite, the bentonite they will shape to become like gravels, like the particles. So the bentonite will be able to penetrate the water surface and continues moving to the bottoms. And after several hours, they will melt and then become stick to be the bentonite or the clay layer. Okay. So that's the methods to do this kind of work. They will not directly using the powder. Okay. So be careful for this work. And after all of the system is filled, and then we need to use in the washing, we are washing and water is bending. There will be several methods. One of that's using this kind of system. They have the heavy, like a metal ball here. and they have a tube, like a tube. So they put this tube in the wells, and then water will go inside this area, and the bowl will be uplifted. So the water can flow in, and after to a certain depth, you stop, and then the bowl will going down to start the opening, and you'll be able to take out the waters. They look like what we use in the baler tube. The concept is like baler tube, but this one they're using for the very relative larger scale. Okay, so use this pipeline to do the same work, and they can use that to clean the dirty waters in the wells. Okay, and another could be you can use in the pipelines. This is the pump. You have the pump inside, and you pump the waters out to let the waters become clean. So commonly we need to do the well washings to let the inside, like mud or some of the small particles, to be washed out. For example, after you do the drillings, you might have the drilling mud. They will stuck in the wells. So you need to have some disturbances to let the mud be destroyed or to be released, and then you will be able to clean the wells to prevent the stuck or stuck of the pore spaces. This is the pipe that I mentioned. They take the waters and then put layer to let the water can be released. Okay. So this one, okay, like a baler tube. Okay. And this one is to pump waters out. And the water, this is for maybe 1 hour, so you can still see they still have the color. So we need to pump for a long time to let the water become clean. But honestly speaking, it's quite time consuming. So sometimes the drilling people, they don't want to spend so much time. So we still need to watch them to let them do the clean enough. And another is using the inject of the air. So this one they inject air. So this one is the air pipelines, and this is the well. So the well is very small, only 1.5 inches, maybe around 1.5 inches. Okay. But this one is also time consuming because you are not able to know if the water become clean or not. But inject the air have the benefit is that I mentioned that the outside we will have the mud, the drilling mud. And you inject the airs will have more strong disturbances to let the mud be released or to be destroyed, and then they can be bring out. So this one they inject the airs. And another could be when you do the drillings, you can also still using the same concept. I mentioned that there's jumbo. The jumbo they inject the airs in the wells, so they can also using the inject of the airs to clean the wells. So sometimes when you do the drillings, you might see the workers, they were doing the like the washings. Okay, they will uplift or put down to let the wells become more clean. So they will also do the inject of the airs. So you can see that this drilling pipeline is relatively small, and previous one is relatively larger. So this one is relatively small. The scale is different. But the jumbo could be the same machine, but the same machine, but they can install the different size of the pipeline. Okay. So after the drillings, you will install the surface as the water project the same. Install the upper part and put some parameters. I mentioned that parameter, yeah, but right now I have not finished the parameter slice preparations, so I'll teach that after that. And as I mentioned that for the groundwater observations, if you do not set up correctly, you might get the wrong result, and the wrong result is garbage. It's not able to be used. Okay, so be careful for that. So very quickly summarize. Well is mainly using for supply water resources, what I mentioned. And in order to understand the groundwater quantity and qualities, the observation wells are installed. So the main wells for the water resources, we want to take the waters. But a company will set up observation system. I'm not sure in other countries, but in Taiwan right now we have a lot of observation system. Because that's a very important part. Although they do not have they cannot earn money. Okay, you spend the monies in the observation, but they cannot let you earn monies. So sometimes government is not want to do this kind of work. Government hope to have the invest the money and then can have the earn money or take back the monies. So there will be the benefit. And if this kind of work do not have the benefit, they might not want to do the work. So sometimes we need to enforce the government or let the government know that this kind of observation well is very important. It can help us understand the hydrogeological system and understand if the water is sufficient or not, or when you do the pumpings, how to manage the system and how to maintain the sustainable use. And groundwater hydrology is the study through the wells to understand the groundwater quantity, qualities, and also for the hydrogeology. So commonly we install the wells, or we try to do the drillings of the wells to understand the groundwater system. But as I mentioned previously, we try to use in the one line and connect to another line and then become the 3D system. And sometimes it's not easy, okay? And remember that the information that we observed from the well is not exactly the same for that in the aquifer system. Although we using the wells to observe the groundwaters, but this point is also very important. What you see the water levels in the wells is not exactly the same as in the aquifer system. We might have the skin effect or the well bore storage effect, and commonly they will have the slightly differences. But they quite depends. For example, if your purpose is the water resources, the several centimeter or several slightly differences do not affect largely. So it's no problem for that. But if some of the specific issue, like you want to detect the finer variations, and the small variation might affect your result, and you need to be careful. Okay. And the other is that the water flow from aquifer to the wells or from the wells to the aquifers, they take time. They are not immediately response. Okay. If you are still systems, the propagation is due to the pressures. Maybe there will be immediate response. But if they are the water flow in and flow out, they take time. It depends on the hydraulic property of the well of the aquifer system. So when we assess the T values, we mentioned, or in the following class, we were talking about the hydraulic test. The T value represent like how fast the water flow from aquifer to the wells. Okay. So if the T value is very small, that means it takes much more time to flow from aquifer to the wells. It implies that your groundwater system have the response, for example, due to earthquake events. The head or the pressures increase immediately in the aquifer system. But in your wells, it takes time to respond. They have the lag. Okay. And like we call the earth tide analysis or tidal analysis, the concept is that they analyze the tidal variance stream, because we know that moon and sun will have the gravity to affect our earth and the waters, right? So we were able to predict the variance change, or the gravity-induced the variance changes. And these changes will affect the water flow. Okay. So when we see the groundwater flow, the groundwater level in the wells, they have the response. But if we compare with the calculated predict tidals, they might have the time lag. And this time lag will imply that the water flowed from the aquifer system to the wells. So they imply the hydraulic property of the wells. Okay. So for the tidal analysis, we can use in the predict the water level and also the observed groundwater levels to assess the hydraulic property. The concept is like that. So barometric pressure is one of the driving force, and tidal is another driving force. So can use in these time differences to estimate the hydraulic property in the system. Okay. So that would be what I mentioned. What you see in the wells is not exactly, or is not immediately represent the aquifer response. They might have the lag, and they might have the differences a little bit. But generally, they're still quite okay to use. And even the quality issue is the same. When we doing the water sample in the wells, we take the water sample in the wells to do the data analysis or the quality analysis. There'll be the requirement. For example, you know the like 100 meters of the wells, and you know the diameter could be 2 inches. So you will be able to calculate how much water volumes in the wells. And for the standard to take the water sample for the data analysis, you need to take out 3 times of the water volumes. And then after that, the water is refreshed, and the water will be able to represent the site property. Okay. So for in Taiwan, or I think in other countries will have the similar rules. If you would like to take the water sample to represent the site properties, you need to repress the volume 3 times, and then you will be able to take the water to do the analysis. Okay, so that's a required standard. You need to follow in that, and then the water quality can be used for some of the further analysis. Yeah, so there'll be another issues. If you do not do that, your water in the well may be contaminated by rainfall, or contaminated by the surface water or some other contents, or even they connect to the atmosphere. They will have some other connections like the oxygen increase. Okay, but the aquifer, if we like to know the oxygen numbers in the aquifer system, we might need to repress the water in the wells, or they directly connect to the atmosphere, or they have the CO2 dissolved in the wells, so your pH value might change. Okay, so they will have some other environmental impact. You need to repress the water, and then you'll be able to assess the water quality for your purpose. Okay, so very quickly for the well constructions, I don't know if you have any questions about the content here. Since the groundwater observation is not finished, so we continue the following talk. And following, we're talking about the pumping test. As we mentioned before, when we would like to assess the hydraulic properties, we have the several methods: laboratory methods, in situ methods, and also the empirical methods. And pumping test is for the in situ methods. And this kind of method is very important because, as I mentioned before, the hydraulic property have the scale effect. Scale effect means that under different kind of scales, your hydraulic property could be varied. And commonly, the larger scale, you will gather the larger values, and small scale, you will gather small values. Because commonly in the larger scale, you will have we call the preferential flow path. The water will easy to flow to this kind of path. So you will gather relative high quantity of the hydraulic properties. And for the small scale, you like some of the material or some of the experiment, like this time you go to the lab to do the falling head test. The material is pure material, right? So they are not exactly the in situ result. And sometimes we use remote methods. You take the sample from the outside in the lab, and then you try to dry the sample totally, and then destroy the samples and remote a specimen to do this kind of experiment. So this kind of remote method will that your original property also changes. Sometimes for the shallow depth, you might have the plane root between. So that kind of space might become like a preferential flow path. But after you remove that, you might take out some of the organic compounds or organic materials. So the material will be more uniform, and then the K value will decrease. Okay. So your laboratory experiment sometimes is not able to represent a real situation. And if you would like to understand more real situations in the field, we commonly need to do the pumping test. Okay, so that's the main purpose. We do the pumping test. But honestly speaking, the pumping test is for a very long time ago. It's proposed by the Thais or the solution from Thais. So there could be several dozen of the years ago, or yeah, so long time. But I'm speaking right now. In the past, we do not have the powerful computers, so we using the ideal condition to do the assessment for the K value or T values. But right now we have very powerful computers, so we should be able to find the new methods to do the estimation or do the inversion. Inversions means that we use the feedback calculation for your K value or your hydraulic properties. So if we are able to have this kind of methods, we can propose a new methods, and then we will be able to have more precisely the assessment or the estimation for the hydraulic property. Yeah, but right now, most of the situation or most of the work we're still using the pumping test. A pumping test is a field experiment in which a well is pumped. Sorry. So the well is pumped at a control rate, and the water level response or the drawdown is measured in one or two surrounding observation wells, and optionally in the pump wells, this control well itself. So commonly when we doing a pumping test, we will have one or two more wells. Okay, pumping wells, we need to have one well is doing the pumpings, and commonly we need to have observation well nearby because we need to know how large your water level decline, and then you'll be able to assess when the pump wells influences your observation wells and how fast the inferences, and then we can use in some theoretical equations to do the assessment. And commonly we will also have the observation for the pump wells and surrounding wells. But honestly speaking, for the pumping wells, the observation is not quite make sense because they will have the we call the well-bore storage effect. So the quantity is not exactly suitable for estimate the hydraulic properties. But the company will still do the observation for the pumping wells. Okay, and the pumping wells commonly collaborate with the observation well, and then we will be able to assess what we call the storage coefficients. Single well, you are able to gather the K value or T values. But if you like to assess the storage values, you need to have the multi-pumping wells. Okay, not pumping wells, multi-well test. That means you need to have at least the two wells. In the later cases, we're talking about the hydraulic, groundwater hydraulic. You will be able to see how this kind of inferences. Okay, you need to have the distance, and then you will be able to assess your S values. Okay. Yeah, so that's what we mentioned. We commonly have this. And response data from pumping tests are used to estimate the hydraulic property of the aquifers, evaluate well performance, and identify aquifer boundary. Okay, so there'll be commonly pumping tests have three purposes. One is to estimate the hydraulic property of the aquifers. That's very commonly used, or commonly we use the pumping test to do this work. But they were also able to evaluate the well performance, although we were not talking about this in the class. Well performance means that when you have a specific diameters, when you have the specific screens, and then when you do the pumpings, how much water you will be able to obtain. They have the limitation because your well already be designed. So the maximum water volumes already be fixed. And your pump, if you're using the small pump or using the strong pump, your efficiency will be different. So the well performance to represent the efficiency of the pump or the water supply in the wells. Okay. Yeah. Although we do not talking this in the class, we're talking about how to assess the water quality, the hydraulic property. And the third part is to identify the aquifer boundary. The same is we do not talk in this too much, but we mentioned in the later class. The aquifer boundary means that when you reach the no-flow boundary or you reach the constant head boundaries, your pumping data, your observation data will be represent different patterns. Okay. In the later class, we were talking about the superposition concept. When you reach the no-flow boundaries, you can imagine that when you do the pumpings, we expect that there will be continuous or unlimited water supply nearby. Okay. But when you have the no-flow, means that you reach the water limitations. So they will not have the water supply anymore at that boundary. So you are able to expect that your water level decline will become larger, right? So that's what you meet. When you see that when you do the ground pumpings, but you see your water level decline, do not have become the steady state condition. They have the decline behaviors. You may reach the no-flow boundary. And when you have another, you continue to have the water level decline, but after some time, they become increase the water levels. That means you have the water supply inside. So that means that you reach the constant head boundary. For example, if they have the water body nearby, or the river nearby, the seawater nearby, they have the additional water to flow into your system, your cone of depression systems. So they provide additional water, not gradually supplied. They have actual water supply. Okay. So you see your water level uplift, not a continuous decline or not the steady state conditions. So your pumping test also able to identify the aquifer boundary. So another example is that you don't know if this area have the fault. So you might be able to do in the pumping test around that area. You expect they might have the fault nearby. So you do the pumping test and to see if they reach the boundary or not. But some difficulty will be fault. Sometimes they are flow channel. Sometimes they are no flow boundary. The fault gauge, if they have the fault gauge, larger fault activities, they will have fault gauge. They are clay, so they become impermeable. But some of the fault channels, they become like a damaged zone. And damaged zone, they'll allow the water to flow easily. So they might become like a conduit for the water supply. So sometimes also not easy to identify if they have the fault nearby or not. But they have the potential to do this kind of work. And aquifer test and aquifer performance test are alternative designation of a pumping test. In petroleum engineering, a pumping test is referred to as the drawdown test. So in different kind of the field, they might using different name or terminologies. So although we might not match that, but you will know, they are the similar concept. Okay, petroleum engineering, they produce the oil and gas. Okay, they will say that's the drawdown test. Like in the geothermal system, we call some of the pumping tests is the disturbances test. They try to do the pumpings and to see how it influences the nearby wells. Okay, and in the pumping test, the concept is the same. Although we are not used that to quantify the hydraulic properties, but they were able to provide you, do the wells have connections or how large connections between the wells. Okay. Yeah, so there will be different terminology, but the concept or the knowledge is similar. The goal of the pumping test, as in many aquifer tests, is to estimate hydraulic property of the aquifer system. For the pumped aquifers, one seeks to determine transmissivity, hydraulic conductivity, that's the horizontal and vertical, and also the storage coefficient. And commonly, when we do the pumping test, we assume there will be only the horizontal flow path. So commonly, what we obtain will be the horizontal hydraulic conductivity or transmissivity. Okay. Although we do not address that, but you remember that commonly we obtain is the horizontal flow patterns or the hydraulic properties. And vertical one will be very, very difficult because we do not have the equation or the system to estimate the vertical flow patterns. Okay. Although we can use in some of the, we teach the equivalent concept to do this kind of calculations. If you know the different depths for the K values, and you might be able to use the equivalent concept if the flow vertically, you can have different K at different segments, and you can assess how the water flows in the vertical directions. Okay. So that could be one of the methods, is the indirect method, but honestly speaking, it's not totally correct. Okay. And storativity or the storage coefficients is another. We commonly use in the pumping test to try to estimate the T and S. So you also need to understand that T and S represent the aquifer property. Okay. They are not for the specific material. They are aquifer property. And aquifer property means that they are a kind of equivalent concept. Or they combine the material together. They do not separate the specific depths. They just estimate that area or that interval, how large the hydraulic property you have. In their systems, one also uses pumping test to estimate the property of aquitar, the vertical hydraulic conductivity, and the specific storage. But we can use in the systems to do this kind of work. As I mentioned, that if we have the aquifer and aquitar together, if we have the aquifer system, perfect aquifer system, 2 layers, unconfined or confined, or two system. Okay, so we do the pumping test here. We do the pumping test here. Okay, so we got the K1, there will be K2, or T1 the same. Okay, T1 that can be calculated using the thickness. So you got a K1, K2, and then you know the thickness. If you know the thickness, you can use in the equivalent concept to estimate like a vertical K of the aquitar system. Or you can use in the if these two observations they have the consistent. For example, the water levels. This well have the like this, and this well have the leg. And you might be able to know, for example, if this is the high head, this is the low head, they have the potential to flow downward. And you can see this one is faster, this is slower. So they imply that you take time to propagate through the aquitar system to the deeper aquifers. So we can also use in the leg to estimate the property of the aquitar system. Okay. So they also have other equations to do these kind of calculations. Now, but honestly speaking, it's just the indirect calculation. It's not easy to obtain directly. And pumping test can identify and locate recharge and no-flow boundaries that may limit the lateral extent of the aquifers as well. So this is what I mentioned. If you have reached the boundary for the constant head, they become the recharge or the no-flow boundaries, you might have the different result. The response for the observation will be different, and you will be able to assess if they reach some specific boundary or not. Okay, we take 10 minutes break.